Hi there, in this video I'm going to take a closer look at the OWON HDS272S Scope meter, which you may have spotted in some of my more recent videos. There are plenty of reviews for this scope meter already out there, and so I decided to focus this one on what I think are the key aspects. Just for the record, what you get with the scope meter: a nice carrying bag, a set of instructions, some software CD, 1x1x10 probe, a USB-A to USB-C charge lead, a pair of reasonable multimeter probes, and 2 sets of BNC to alligator clips test leads. The manual is not too bad. It has decent safety warnings which are important for this scope, but the description of how to use it is more or less a list of the function keys. If you already know how to use a scope, multimeter or function generator, you will be fine. If not, this manual is of no help, which is a bit of an opportunity lost. The manual covers all 4 models currently offered. I have the top one, HD272S, which is supposed to go to 70 MHz bandwidth and has the signal generator option. I already have a Rigol 1054Z scope, so why did I buy this one? I got it for 2 reasons. First, it's convenient if I already have some device on my bench and I want to show you a scope picture at the same time. It's a lot easier than setting up my Rigol scope for such shots. But of course, the little scope has only 2 inputs and has no decoding options, so sometimes the Rigol is the only option. The second reason is that it can operate battery powered, and in that mode it's completely floating with respect to mains ground. This is a lot safer when examining mains powered devices, which at least in some parts have a direct path to mains. In this circuit here I have connected the probe tip to a diode on the primary part of this switch mode power supply, and the probe is directly connected to the mains neutral, but that is so risky I would never do this with a mains powered scope. Probing a circuit that is directly connected to mains is always dangerous, but far more so when using a mains powered scope, because the probe ground lead of a normal scope is always connected to mains earth. This means through your probe you may cause a short circuit between mains live and ground. At the very least you probably destroy the probe you are holding in your hand and quite possibly your scope as well. In anticipation of its use to measure mains powered circuits, OWON recessed the BNC sockets of this scope and surrounded them with black plastic, both commendable measures to make accidental touch of exposed metal, which could be at mains voltage, more difficult, but as you can see, not impossible. We have the 2 input channels of the scope and the output of the signal generator. Of course, this touch protection, as far as it goes, needs the BNC connectors to be isolated as well, and I'm pleased that the probe that OWON included meets this challenge. Once connected, it is well protected against touch, and even the access for the compensation cap is deeply recessed. The protection against touch isn't as good for the unused ports. I would have liked to see some plastic caps for those, but sadly no. In ×10 mode, the probe spec says it's good for 70 MHz and 600 volts PK, which I assume stands for peak, not peak to peak. So that would be slightly more than 400 volts RMS. Although this is a 2-channel scope, OWON only provides 1 probe, but added 2 of these cheap BNC to alligator clip cables, and their BNC connectors are of course not isolated at all. Using any of these in a high voltage situation is an absolute no, even when the connection to the high voltage circuit is made through a proper probe on one of the other ports. On the side, a flap hides the USB charge port, a connection to signal ground for the scope, and the usual 1 kHz square wave output for probe compensation. For a quick check of what's referenced to signal ground, I clipped the test lead on the terminal in the side panel and the other end to the multimeter in continuity mode. As expected, the grounds of all 3 BNC sockets, 2 inputs and 1 output, are all connected to the same signal ground. This is something you need to consider when using multiple channels and or the signal generator. The shield of the USB cable that came with the unit is also connected to signal ground, and so is the ground of the USB supply voltage. This means if you charge the scope or connected to a mains powered PC or laptop, you have lost the scope's isolation. This can be pretty dangerous and catch people unaware, especially if they use a PC or laptop not for charging but with the OWON's Windows only software for reading the scope remotely. The manual explains this and adds good drawings, but I think a few more words of caution for newcomers would have been good, in particular on why probing anything with serious voltage that is also earth referenced is so dangerous. The multimeter sockets are completely independent and not connected to signal ground, which is a good thing, or else you would have to worry about not touching any test leads left plugged in. One last thing about signal ground, I found that some, but not all of my BNC cables had problems making a good ground connection because of that plastic shield OWON added over their BNC sockets. If you experience weird signals coming in or out of the scope or a signal generator, try this trick and add a lead to the signal ground port. Let's have a brief look inside. The tilting bail, and especially the way it snaps into position, looks quite frail, and I wonder how long it will last. The lid of the battery compartment is held with a single screw into a metal insert, which is nice. The lid is kind of recessed and not the easiest to grab for lifting. Eventually it reveals two 18650 cells in parallel, each according to the manual rated for 2200 mAh. I did test this claim, and one had 2080 and the other one 2088 mAh, so somewhat less than claimed. The manual also states they last 6 hours, which isn't true either. About 3 to 4 hours is my experience, depending on what you do. The batteries charge very slowly, with just 1 amp draw at 5 volts. That's just 0.5 amps per cell. The meter itself draws 0.6 amps in operation, so when charging while running, the total current is about 1.6 amp. I think OWON should have added a fast charge option. As it's now, the slow recharge creates the temptation to keep the scope meter plugged into the charger, which, as you know, means it's no longer isolated. Anyway, going deeper and removing the 4 self-tappers, the enclosure separates easily. A quick glance at the insides. I'm not taking the board out if I don't have to. Anyway, I don't think there's too much to learn from the other side. The front end of the scope is under this shield, which is soldered onto the PCB. 2 caps fixed with some glue. While the black one looks planned, I'm not so sure about the green one. Of note, some kind of debug connector, providing a list of signals that may be interesting for hacks. The multimeter input section. A few interesting things here. The 10 amp fuse. As usual, there's the space for a decent 1000 volt rated one, but they skimmed and put a shorter holder in. Well, at least the provided fuse is ceramic and rated for 600 volts, which actually matches the CAT rating printed on the front. Some tracking slots, but in general there is not much of input protection visible. The yellow block here is a 250 mA fuse in line with a 1 ohm shunt for the 200 mA range. It looks like a resettable fuse, which would be a good thing. The 2 black boxes are relays. The HDS272S series has 3 modes. There's the multimeter, of course, with its separate inputs that we just examined. It's 20,000 counts and, let's say, reasonable but nothing special. You don't buy this device for its multimeter. Then there is the function generator, which is off by default, so you have to turn it on separately. Once you do, it continues to run while in scope or multimeter mode, which is quite handy. And finally, we have the scope mode with 2 channels which can be turned on or off separately. I'm not going to show how to use each of these modes or the quirks of the OWON user interface. Instead, I will focus on the performance. Let's start with the scope, which is probably the most used mode. My first question was, how accurate is the time base? To test this, I'm using my GPS discipline oscillator, GPS-DO, which I can set to produce nearly any frequency between a couple of 100 Hz to over 800 MHz with excellent precision. I'm using a direct input to the scope with 50 ohm termination. Here I have set it to 1 kHz, and with 100 microseconds per division, one period of the signal should be exactly 10 squares long. I mark this with the two vertical cursors, A and B, and as you see, this is indeed the case. I also enabled the built-in measurement function to show the frequency, and it reports 1.000 kHz as it should. Going to 10 kHz, and after adjusting the time base to 10 microseconds, one period of the signal is again exactly 10 squares long. 100 kHz at 1 microsecond time base, while timing wise is fine, the corner of the squares start suffering a little. 1 MHz at 100 nanoseconds time base, and the timing looks good, but now we really start losing the sharp corners of the rectangular wave, indicating we are definitely losing some of the higher harmonics due to the scope's bandwidth limits. 10 MHz at 10 nanoseconds time base, and the signal looks pretty terrible. The scope has trouble getting a consistent trigger, so in auto mode the picture becomes washed out. In single mode we get a static but much clearer picture. From that I think it's fair to say the overall period is still 10 squares, so I rate the 10 nanoseconds time base setting as accurate. For comparison, here's the same signal on my Rygold 1054Z, which is nominally 50 MHz but tweaked to 100 MHz. At 20 MHz now, and it's certainly not getting better. Doing a few single shots, and I think I rate 5 nanoseconds, which is the fastest time base, still as accurate. 50 MHz now, and not much left of a rectangular wave compared to the Rygold at the same frequency. A far less demanding test is using sine waves, but my function generator can only go up to 50 MHz and is definitely not as accurate as a GPSTO. Anyway, let's see what the picture looks like. This is 10 MHz, which is nice enough. 20 MHz still okay. 40 MHz looks fine. 50 MHz looks okay. That's as far as I can test using sine waves. The conclusion is that the time base and frequency measurement function of the HDS272S is accurate, but the 70 MHz bandwidth is a pretty hard limit. It kind of works for sine waves, but more complex waveforms with higher harmonics degrade seriously, and 40 MHz is probably the limit where you can still the difference between a sine signal and one that isn't supposed to be sine. The next question I wanted to know is how linear the horizontal amplifiers are. A quick way is to sweep a sine signal from 40 kHz to 40 MHz and observe how much the amplitude changes. I put two horizontal cursors marking the wave's initial amplitude, and as you can see, only at the very high frequencies the reducing amplitude leaves a small gap between the displayed wave and the cursors. This means the amplifiers are quite linear over this wide range. Of course, they might be very linear but still wrong in value, which is what I looked for next. I choose 100 kHz as frequency because at this value I can still compare its AC volt readings with some of my multimeters like the Agilent 3441A, the HP 3478A and the Bryman 869S. However, at the highest sensitivity of 10 mV per division, values are tricky to measure because noise gets easily introduced. It is easier at higher amplitudes where the signal to noise ratio is much higher. Basically what I do here, somewhat accelerated, is gradually increasing the signal strength, adjusting the vertical sensitivity accordingly, and reading the measured voltage on the scope and comparing that with my control multimeters. The result is this graph. The blue trays are the OWON measurements and the green one the control. Ideally they should be right on top of each other, and they nearly are. I overlaid the error as the red trace. Its scale is on the right y-axis. The only vertical accuracy value listed in the spec is the DC accuracy with ±3%. This here is AC, but for most of the range it does fall into the ±3% band. The increase of the errors towards low signal values is probably due to the noise making accurate measurements impossible. For completeness, I decided to measure the vertical accuracy in DC, although one has to wonder how often DC is measured with a scope, but I ran into problems. Here I am feeding a clean 10 mV DC signal into the OWON and the Bryman 869S as control, The video is very shaky because I'm holding a tablet to film this. Watch what happens when I switch the main camera on. The OWON is extremely sensitive to noise, in this case from the DC to DC converter I'm using to power my camera from a USB bank. At higher voltages like 1 volt here, I can use my main camera because the noise is now invisible. Here you see another problem, one of the real grievances I have with the HDS272S. The 1 volt signal at 200 millivolt per division is 5 squares up, so just at the very top of the screen. The readout is 984 millivolts, which is an acceptable error of around 1.6%. Watch what happens when I change to 500 millivolts per division. That line should be on top of the second row of squares, but is noticeably lower, and the readout at 850 millivolts is a whopping error of 15%. If I change the scale further to 1 volt per division, the line is still slightly below the expected 1 row up, and the error is now slightly less, 10%. In all this, the input signal has basically not changed except for a few microvolts. This error comes from the extreme temperature sensitivity of the HDS272S. The manual says if there is a temperature change of 5 degrees Celsius or more, you must run the auto calibration. That 5-degree change is practically guaranteed when you use the scope for more than a couple of minutes because it heats up internally. To do the auto calibration, you need to disconnect everything that is connected to the scope first. Autocall takes around 1 minute and I'm showing it accelerated. At the end it sets everything to defaults, so you may want to save your setup first before doing it. After the auto calibration, the 500 millivolt setting is on the second horizontal line as it should, and the readout of 974 millivolts is an error of 2.6%, which is within the spec. The 200 millivolt setting is still correct on the fifth horizontal line, and 1 volt per division shows the signal on the first horizontal line as it should. After auto calibration and for some time after, the vertical system of the HDS272S is certainly within the ±3% specified. But you have to get into the habit of performing auto calibration every time it has been used for a while, and certainly before you want to rely on any vertical readouts. This sensitivity is really annoying, and I'm not sure what the underlying cause is. Probably some parts have a significant temperature drift which hasn't been compensated to save a bit of money. The other issue is how sensitive the HDS272 is to noise at high gain settings of 10 to 50 millivolts per division. Okay, the DC to DC converter I use for my camera isn't the cleanest, but I don't have this noise problem with other devices. The HDS272S seems to be particularly sensitive. And on that note, onto the signal generator. You can, of course, use the HDS272S to view the generated signals as I'm doing here. You have to feed the generator output B and C to one of the scope inputs to do that. The trouble is that to change anything in the generator you have to switch yourself through the unwanted multimeter screen, which gets a bit tedious if you need to do it a lot. So I'm going to show the waveforms on my trusty Rigol. The generator has 4 standard waveforms. Here's sine, now square, triangular called ramp, pulse, which at a selected frequency and pulse width looks like a square wave, sorry about that. Following this we have arbitrary waveforms and lots of them. The majority must have been added fairly recently because neither the printed nor the manual on CD or the downloaded one lists them all. Now these are often found in function generators, and I think it's mostly because they have mathematical definitions and those equations are fairly straightforward to plot and convert into a pattern for an arbitrary waveform. The question is whether the waveforms are of any practical use. To be honest, besides the common sine, square, pulse and triangular, the only time I've used other waveforms on my function generators was to test how a multimeter's RMS function deals with the weird waveforms. I spare you seeing the most boring test, namely checking the frequency accuracy. As you would expect from a generator where everything is digitally derived from a master clock, the frequencies are highly accurate over the whole range. From 0.1 Hz to 5 MHz I used the square wave, but that tops out at 5 MHz. So for the rest, up to 25 MHz, I switched to sine wave. Next, I was interested in how accurate the amplitude of the generator is. For this test, I picked 50 kHz, which the BM869S can still comfortably measure, and slowly increased the generator amplitude using the high Z setting. The value on the OWON is volts peak to peak, but the BM869S measures RMS, so one has to divide the VPP value by 2 times square root of 2 to get the equivalent RMS voltage. In this plot, the selected volts peak to peak is on the x-axis, while the y-axis shows the percent error of the measured value against the equivalent RMS value. The BM869S test you just saw is the red curve, which is generally within plus minus 1% except for very small values of 0.02 volts to peak, where the error is way off. That is because the BM869S, in line with most true RMS meters, needs a minimum voltage to give accurate readings. In this case, the stated accuracy is only valid if the signal is at least 10% of the range. If it is between 5 to 10%, an additional error applies, and below that, all bets are off. The most sensitive range is 500 millivolts, so 10% is 50 millivolts, 5% to 25 millivolts, but 0.02 volts peak to peak is just 7 millivolts RMS, so no wonder that the error goes off scale. The blue trace is the same test, but using the Agilent 34401A instead. This bench meter has similar caveats as the BM869S. For the 34401A, the AC signal must be at least 5% of the range, but in this case, the lowest range is 100 millivolt, so 5% is 5 millivolts, and therefore the 34401A can measure a 7 millivolt signal with some hope of valid results. I found repeating the same test with different meters quite interesting. It really shows that for demanding measurements, one needs to consider what meter to use, know their specs, and consider their shortcomings. As far as the amplitude accuracy of the HDS272S function generator is concerned, OWON has not stated any accuracy values in the spec, but I think looking at the blue trace it is acceptable. In this kind of graphs, errors tend to rise towards the left purely because of the way error percentages are calculated. By the way, I have done the same test for 50 ohm loads and it was the same results, except all amplitude values are halved, of course, because the function generator has an internal 50 ohm impedance. The next question is, how stable is the amplitude over the frequency range? To know this is important if you want to use a generator for testing frequency range of multimeters or amplifiers. I'm using my Rigol scope to verify the output voltage of the HDS272S generator because it's the only thing I currently have that can measure AC voltages across this frequency range. Again, OWON does not specify anything how stable the amplitude is supposed to be, but the results are actually quite good. The generator is very stable. It only starts to drop beyond 10 MHz, but the drop is still less than 1 dBm all the way to 25 MHz. If you wonder about the zigzag, this is an artifact from using the scope's built-in measurement function for RMS, which is basically based on integrating the square of the voltage samples. This means the accuracy varies inevitably with the number of periods sampled. You need to get at least one period on the screen, but more are better, but then again not too many because otherwise the resolution suffers. In practice, this means as you increase the frequency, the number of periods included in the calculation increases. But then comes a moment where you switch to a faster horizontal time base, which reduces the number of periods used in the calculation, and that causes a small change in the value, which are the spikes in the result. Of course, when doing this kind of measurements with a scope, I always try to keep the number of visible periods as constant as possible over the whole frequency range to reduce the effect. But over such a wide frequency range, some occurrence of this effect is pretty much unavoidable. Apart from sine and square, the generator has a very useful pulse mode. I had a quick look at how well it works. The pulse width is set to 25 microseconds, which is confirmed by the use of my frequency counter. Now 20 microseconds, 10 microseconds, down to 1 microseconds pulse width, and now down to 100 nanoseconds, all working as it should. Here I set a fairly large rise time of 4 microseconds for a pulse of 10 microseconds duration. The fall time is set to 15 nanoseconds. A quirk in the user interface does not allow removing the 5 nanosecond part. The actual rise time as measured by the counter is slightly larger, but since OWON has not specified any tolerance values, you have to accept these inaccuracies. At least the fall time is pretty accurate. This is how the signal looks on the Rigol scope. Because of the relative long time base needed to capture the rise time, the scope can't measure the fall time accurately and can only state that it's less than 80 nanoseconds. Let's change the fall time as well and make it a nice symmetrical signal. Okay, and with that I think I verified the most important aspects of the function generator in the HDS272S. Let's move on to the third mode, the multimeter. Nobody is going to buy the HDS272S because they wanted a new multimeter, and I think that justifies that I shortened the usual tests a bit. I tested the DC voltage against various voltage standards that I have, and the results were all within spec, which is plus minus 0.3% plus 5 digits. Resistance against my 0.1% references was also okay. The meter has a good rel mode for very low resistances, and auto ranging is quite fast. Having a 100 megohm range is nice. Continuity is responsive enough. In diode test, the HDS272S can measure 2 normal diodes in series and shows the forward voltage for 1 red LED but not 2 in series. It can light a white LED but does not show the voltage. In capacitance mode, the values of 1 nanofarad and below are reading too low, but all other values are within spec and auto ranging works well as opposed to my other OWON meter, the XDM1041. A quick test of the DC milliamps shown sped up to save time. I compare the readings with my Brymen BM869S. It looks close enough. The accuracy of the Brymen is 0.5% and the HDS272S is 0.8%. Of note, there is only one low current range on the HDS272S, 200 milliamps, and that is it. The same test for amps. The Brymen is still 0.5%, but the HDS272S single 10 amp range is specified as 2.5%, but it defies that mediocre rating and is almost as accurate as the Brymen. The same is true for the AC amps, so I skip this test here. A quick check of the AC millivolts with the Brymen at 0.7% and the HDS727 at 0.8%. I think they are close enough. I really like how quickly the HDS272S settles. The BM869S takes always an annoying long time to get to a final value. This was a sine wave at 100 Hz. At 1000 Hz, the HDS272S is still in the game, but it's specified only for 1 kHz, so when going beyond that, the values drop fast. A check against the square AC output of my DMM Check Plus standard reveals 2 things. First, the HDS272S is actually a true RMS meter, although strangely that fact is very well hidden in the manual. Secondly, the Brymen is just 0.04% off the correct value of 4.9989, while the HDS272S is 0.54% off, which is actually slightly outside the 0.5% part of the spec, but the additional plus 10 digits in the spec means it's actually still inside. So overall, what to make of the HDS272S? Is it a good buy? Let's start with the multimeter, which is probably the least used part. I mean, the meter is quite fast, reasonably accurate and easy to read, but I would not call it robust, because it has too little in terms of input protection. Used as a pure multimeter, its battery consumption is enormous compared to normal multimeters, because all the other electronics for scope and function generator are always powered on as well. On the other hand, the fact that it's there and just a push of the mode button away, if you need it, it can be very useful if you have no other meter around. I'm actually quite impressed with the function generator. The only thing I'm missing is the sweep function. The generator is pretty accurate, stable and fairly straightforward to use. It is a very useful add-on, especially in a portable format. Since it's optional, I definitely recommend paying a little more and getting it. The main purpose of the HDS272S is of course the scope. Overall I like it, but as with most instruments, it is important to learn about the quirks and limitations, and there are a few. Apart from the weird user interface, the most annoying one for me is the temperature sensitivity of the horizontal amplifier, requiring frequent auto-calibration cycles. Then there is the sensitivity to electrical noise, making measurement of very low signals a challenge. Overall, I do not regret buying the HDS272S. It's the 3 most often used test devices rolled into one portable and battery-powered format. While playing around with the HDS272S, I found a neat way to measure audio amplifiers. But as this video is already quite long, I leave that and a look at the software CD that came with it for a later video. If you have not subscribed already, hit that button and the notification bell so you don't miss the next video, and maybe consider becoming a Patreon, link in the description. As Patreon you get early access to videos, a blog and other exclusive content. Thanks for watching.